Okay, let's do week 4 example problems. So the very first one is a computation of the number of Schottky defects. Remember, Schottky is when you have a vacancy of both the cation and the anion at the same time in KCl. Okay, so we're given this information. So we're asked to calculate the number of Schottky defects per cubic meter, which is how you calculate the amount of Schottky defects. It's not, oh, I have this amount of Schottky defects. It's based on, oh, I have this amount of Schottky defects per cubic meter. And the same thing for calculating the amount of Frankel defects in potassium chloride at 500 degrees Celsius. The energy required to form each Schottky defect is 2.6 electron volts, whereas the density of KCl at this temperature is 1.955 grams per centimeter cubed. Okay, so the very first thing we need to do is that we need to calculate the amount of lattice that we can possibly have these Schottky defects. So, first step, find n, which is the number of lattice, because really these defects happen at these lattice. Lattice, uh, lattice sites. Yes. All right, so this is used with the equation n is equivalent to Na times P. P is the density, all divided by the atomic weight of K, because that's the cation in this case, plus the atomic mass, atomic weight of chlorine, which is the anion. So let's calculate this now, shall we? So Na is just Avogadro's number, which is going to be 6.022 times 10 to the 23rd atoms per mole. So that is the first part of that. And then that's going to be multiplied by the density, which we are given to be 1.955 grams per centimeter cubed. 5 grams per centimeters cubed. However, we cannot leave it in centimeters cubed because it's asking us to find it in per cubic meter. If it asks us to, find the number of Schottky defects per centimeter cube, then we can leave it there like that. But we're asked to find it in per meter cube. So we have to use a conversion factor. And what I'll do here is that I know there's going to be 10 to the second, which is just 100 centimeters in 1 meter. Well, you might be thinking to yourself, well, that doesn't really cancel out because I'm going to have centimeters squared on the bottom. And you're right, it won't cancel out as it is right now, which is why I'm going to raise it to the third power, which makes sense because I'm dealing in terms of volume. So I will want to raise things to the third power. And you'll see that the centimeter cubed will cancel out and we now have meters cubed. However, one important thing that you should note is that this 10 to the second will now become 10 to the sixth. So just keep that in mind when you're dealing with calculations. Do not forget about that. Do not forget your exponent rules, please. And that's going to be all divided by 39.1 grams per mole for the molar mass of K, potassium, plus 39.45 grams per mole for the chlorine. So then once I put everything into my calculator, I should be getting 1.58 times 10 to the 28th lattice. I'm just gonna put lat for short per meters cubed. Now I have the amount of lattice that I have within this salt KCl within a certain temperature. However, I'm trying to find specifically the amount of Schottky defects. So then what I need to do is that I need to do NS, which is the amount of Schottky defects, is equivalent to N, the amount of lattice I have, multiplied by negative QS. Negative Q referring to um, the energy required to form each Schottky defect, divided by 2kT, where K is a constant, where QS is the energy required to form a Schottky defect, which we're given to be 2.67 or 2.6 electron volts. And K is a constant. That constant being 8.62 times 10 to the negative fifth electron volts per Kelvin. And then because this is per Kelvin, we're going to want to work in Kelvin. So then we're given the temperature in Celsius to be 500 degrees Celsius. So then to find the Kelvin of that, just add 273 to that, which is going to be some number. Let's calculate that. 500 plus 273, 773 Kelvin. Okay, so then let's just plug things in now. And we should get, taking your answer from this part over here, I have 1.58 times 10 to the, what was it raised to? 28th? 28th. So that's that value over there divided by negative 2.6 electron volts multiplied by 2 multiplied by 8.62 times 10 to the negative fifth multiplied by 773 Kelvin. I'm not going to put the units first time. And then once I put that into my calculator, I should be getting nope, 5.31 times 10 to the 19th Schottky defects. So I'll just put S for short. Defects per cubic meter. So then that'll be my final answer. All right, so then that's the first question. Let's go on to the second question. I'll change my color. So the second question is asking, can Schottky defects exist in K2O? If so, briefly describe this type of defect. If they cannot exist, explain why. Okay, well, first let's talk about what do we mean by a Schottky defect. Well, a Schottky defects means we have an anion vacancy and a cation vacancy. Vacancy of both the positive charge or cation and sorry, I'm just getting emails, negative. So, okay, so then in this case, we'll have this cation charge over here will be 2K plus and O2 negative. So, but the problem here is if we have each of these parts gone, if you have each of these parts gone, both the cation and the oxygen, well, the problem is that with the vacancy of both the cation and the anion, it's only going to take away one of these cations. So then we're going to be left with an overall charge of +1 due to the leftover potassium. And the problem with that is that we do not have electrical neutrality. And due to this lack of electrical neutrality, therefore, a Schottky defect cannot really exist within K2O. So therefore, no. Because of the fact that based on the definition of a Schottky defect, we need to get rid of one K plus and one O2 negative, but that's going to leave behind this K plus, and it's not going to be electrically neutral. Third part, let's change my color to, let's do purple. All right, so we're going to determine the possible point defects types in NaCl due to the presence of Ca2 plus ions. So if electron neutrality is preserved, what point defects are possible in NaCl when calcium 2 plus substitutes for Na plus ion? How many of these defects exist for every Ca plus ion? Well, sorry, we're not going to answer the second part. That's not very important. The main part I want to get over here is what are the possible point defects we can get due to this presence of Ca2 plus, which is an impurity. And the problem that, or the reason why we need to introduce defects in the first place is that if we replace Na plus for Ca2 plus, we have a net charge I'll put C, of +1. Therefore, we do not have electrical neutrality. So then what we want to do is that we want to try and make this thing more negative. Well, two possibilities we have, and I'm sure there's more, but these are the first two that came to mind, is to remove Na plus. So we're going to have a vacancy. So we're going to have a vacancy. And another possibility is to add Cl minus into an interstitial. So then those are some possibilities that you can have. So relatively simple question. Next one, or next two, I guess. So the next one we should cover is 12.29. Calculate the fraction of laticites that are Schottky defects for cesium chloride at its melting temperature, 645 degrees Celsius. Assume an energy for defect formation of 1.86 electron volts. Okay, so let's just go to our equation over here. Let's do this in yellow. A little hard to see, actually. Dark blue. Well, let's go to our basic equation over here. E raised to, oh, and I just realized, in one of the examples over here, I believe it was this one over here. This is going to be multiplied by E raised to this. Like the E will have the exponent, but then not the actual number of lattice points. Sorry, that was my mistake. And I'm just going to make sure you do not do the same mistake as I did and make sure that the E is being raised to that exponent. Yeah. So back to this question over here. That's going to be the number of laticites multiplied by E, which is raised to that exponent that we are familiar with. Qs divided by 2kT. Well, what we can do here is that we can divide this entire thing by n to get ns divided by n is equivalent to E raised to negative Qs over 2kT. And this matches with the descriptions of the question because it's asking for the fraction of laticites. So we have the total number of laticites over here that are Schottky defects represented with this number over here. So then essentially what we need to do is that we just need to plug in the values for the right-hand side. So then that's going to be E raised to negative 1.86 electron volts, because that's the energy it takes in order to form the Schottky defect, divided by 2 times 918 Kelvin, because remember, you're taking the degrees Celsius, adding 273 to find Kelvin, which in this case was 645 plus 273, multiplied by 8.86, sorry, 8.62 times 10 to the negative fifth electron volts per Kelvin. So then if we just plug this into our calculators, we should get 7.9 times 10 to the negative 6. So this is our fraction. And you might notice that there's a very, very small amount of the total laticites that are actually Schottky defects. So it's a very, very small fraction, as indicated by the very small number. All right, last question. Let's do this in. Yeah, let's do this in black. Yeah, let's do black. So then for the very last question, we're calculating the number of Frenkel defects per cubic meter in silver chloride at 350 degrees Celsius. The energy for defect is 1.1 electron volts, whereas the density for AgCl is 5.5 grams per centimeter cubed at 350 degrees Celsius. So it's essentially the same thing as the very first example problem, except we're just working with different numbers. And the main difference between NS, so the equation for NS, and NF, which is the number of Frenkel defects, is that the number of Frenkel defects is going to have a different QS value. because the energy of forming a Frankel defect as opposed to a Schottky defect changes. It changes. So it's not the same. So in this case, it's going to be what was it? 1.1 electron volts. So essentially you're just going to be plugging into the equation N times E raised to QF divided by 2KT. And remember, N is equivalent to the Avogadro's number multiplied by the density of, I think it was AgCl, divided by the molar masses of silver plus chlorine. So remember this value and you're essentially just plugging into the formula, and you're going to be following the exact same format as the very first example over here. It's just make sure you change the value. So remember, make sure you have this conversion factor because we're being asked to do this in cubic meters. The density changes. In this case, it's going to be 5.5 grams per centimeter cubed. Avogadro's number does not change, and these values over here change because we're dealing with chlorine, so chlorine stays the same, but silver has a mass of 108 grams per moles. And then remember this case over here, T changes because it's 273 plus, in this case, 350 degrees Celsius because that's what we're working with, which gives us 623 degrees Kelvin, and K stays the same, and QS is no longer QS, but QF, which is the energy of formation for Frankel defects. And in the end, you should be getting 2.21 times 10 to the 24th Frankel defects. So I'll put F defects per cubic meter or meter cubed. All right, so then that's it for week 4 or this week. Yeah, I'm pretty sure this is week 4. As always, if there's any questions on the P set or just the last lesson in general, please let me know and I'll catch you guys later.